Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off, where we were describing how we can actually convert the equivalent circuit which we had drawn for determining the parameters of the equivalent circuit, for which we said can be done using either open circuit test or block rotor test. Now once we have all these parameters, the next plan was to build a simulation model, and for that I had described how we can use or how we can approach this process. That is, how we can approach this process of converting any physical system using the knowledge of physical phenomenon, converting that into equations, and then creating a mathematical model. So in this lecture, we're going to start writing equations for this purpose. So as before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length videos that you can access on my own website, which is pythonpowerelectronics.com. That is pythonpowerelectronics.com. To access the list of courses, you can click on this button called Learn. So this is the page with all the courses which I have, and currently I have 5 courses altogether. So I'll go through the courses. The very first course is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and Python packages like the SciPy and the signal package within SciPy to analyze and design filters specifically for power engineering applications. The third course is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can simulate magnetic components like inductors, coupled inductors, and transformers using Python and Python Power Electronics. The fourth course is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python packages like SciPy and the Python control package within SciPy to analyze and design controllers specifically for power engineering applications, taking the example of a single phase converter connected to a single phase grid. And the very last course I have is a free course called Why Specialize in Power Electronics, and this course is specifically designed for either junior undergraduates or high school students to motivate them towards power electronics by telling them about the challenges and opportunities available in the domain of power electronics. So all these courses have been hosted on 2 platforms, which is Decibels Labs and Udemy, and if you click on any of these buttons, it will take you to the course link. So the link for this page is provided in the description of this course, in this video. If you're interested, do check out the description of this video. So with this, I'm going to get back to the lecture. So let me just go over to this diagram which shows you the construction of an induction motor, and I have gone through this several times in the past few lectures. So if you want to know about this, please go refer to the previous lecture. So we are now going to create an equation, or rather a dynamical model for this entire motor. So let's start writing dynamical equations. So those dynamical equations are going to be slightly different from this equivalent circuit. The reason is this equivalent circuit is more of a steady state equivalent circuit. This is extremely useful to determine the steady state operating condition of an induction motor. Right? And this is very useful, and it is used very often in analysis to determine what would be the speed, what would be the efficiency, and so on and so forth. Right? However, if we want a dynamical equation, then in that case we need something which is more time variant rather than something which is more steady state. Right? So this is what we're going to do in this lecture. So let me go and add another sheet and tell you how this is. So as before, we're going to start with drawing a circuit. So we are going to start in a very similar manner, just like this. We are going to start with the stator circuit, and we're going to start with the rotor circuit. So in the most general terms, we can consider the stator as follows. So let me just draw. I think this is good enough. So let me represent this as the stator and this as the rotor. It's just a schematic. For now, let us consider both the stator and the rotor to receive a voltage. Let me say this is Vs and this is Vr. Now, in the specific case of a squirrel cage induction motor, right, we know that there is no voltage which is applied to the rotor. Why? Because the rotor consists of bars which are short circuited on both ends, right? So therefore there is no applied voltage to the rotor. There is an induced EMF, but there is no voltage which is applied. Voltage will be applied in the specific case of a wound rotor induction motor, where the rotor consists of a winding similar to the stator, right? And this winding is usually accessible using slip rings, and you can apply a voltage to it. But in this specific case, there is nothing. But let us consider the general case where there could be such a voltage, and that voltage is VR, right? So now that we have come here, of course, we know that this stator has a resistance. This is the winding resistance, and this winding resistance is exactly the same as this resistance RS here, right? Because this is merely the winding resistance of the stator. Similarly, we can say there is also winding resistance of the rotor, right? We'll call it RR. Well, not very nice. Let me write RR like this, right? And let me just write RS like this as well, right? So you can see that this RS and this RR are actually very similar, right? Now you might be a little confused. You might think, what about this S? But remember, this S is the reason why this S came into account is because we decided to divide the entire rotor equivalent circuit by S to remove the frequency dependent terms. So this is not really something that exists, right? Do not think that the rotor resistance is divided by the slip in order to actually arrive at the rotor resistance. This is something that we had done to be able to merge the rotor circuit with the stator circuit, so that we now have both stator and rotor circuits at the same frequency. But this is a mathematical construct. In reality, the rotor resistance is just RR dash, right? Now here I'm just writing RR because we are saying these two circuits are different. But later we can merge these as before by transferring all the rotor equivalent parameters to the stator. This is something we can do. We can do it later. So now that we have the stator resistance and the rotor resistance, we just have to add to this the stator inductance and the rotor inductance. Alright. So this is a very simple equation. We have here a voltage applied to the stator. That voltage applied to the stator, when there is a current flowing through it, it will have a drop across the stator resistance, and the rest of it that flows through the inductance, which will produce a flux. And the same goes for the rotor. The current flowing through the rotor, there will be a drop across the rotor resistance, and the rest of the current that flows through this inductance will now produce a rotor flux. So there is a stator flux, there is a rotor flux, exactly like we talked about before. And we can write these equations as well. Vs minus, let me write Is into Rs minus Ls into dis divided by dt is equal to 0. This is our stator equation. Similarly, we can think of a rotor equation. Okay, now this is automatically converting everything, but here, since it is a dynamical equation, I will write all the variables as small, right? So Vs, Vr, these are all with small letters, and this implies that these are actually time varying equations, right? Typically when we use capital, it means they are RMS. When we use small letters, these are actually time varying variables. They are, you can say, sin omega t or cos omega t. And we can write the same for the rotor, and rotor di by dt, dir by dt is equal to 0. And let me put a multiplication sign just to be clear that these are actually multiplied. Right. So these are our equations. So we have the stator equation, we have the rotor equation. Now, as we already said before, the flux, right? The stator flux is produced by the current flowing through the inductance. This is rather, here you must say the stator flux linkages, right? So we are talking about the stator flux linkages and the rotor flux linkages, right? Now, the total stator flux linkages is determined by the current flowing through the inductance. As we already said before, not all of this current flowing through the inductance will produce a stator that associates in the air gap. Let me go back to the circuit here. The current flowing through the stator windings will produce two types of fluxes. There will be fluxes which leak into the air outside. So these are not fluxes which actually go into the air gap. So therefore those fluxes which leak into the air do not do anything useful, but they are produced. Similarly, the rotor. The rotor will also produce some amount of flux which leaks away from this air gap somewhere else, right? Don't worry about where, somewhere else. It could circulate somewhere local, whatever. It just is not doing anything useful by producing a flux in the air gap. This exists for both the stator and the rotor. So therefore, what we can do is we can split up this equation, this inductance, as LLS and LMS. And the same goes for the rotor as well. We say LLR and LMR, right? So we now say that this inductance leakage LLS is the leakage inductance of the stator. The current flowing through this produces a leakage flux, and the same goes for the rotor. This inductance LMS and LMR, these are the magnetizing inductances. The current that flows through them produces a flux which now links with the air gap. Right. Now, let's now try it. We can always split this up. We can expand this and write it. I won't bother writing it because it's a pretty simple equation. But what I am going to do is, now, because of this, remember this is a magnetically coupled circuit. In any magnetically coupled circuit, the flux that is produced, the flux linkage. So for example, if I were to write the flux linkage, this flux linkage is not only due to the current that is flowing through the stator, but is also due to the current flowing through the rotor. Always, in any mutually magnetically coupled circuit, that is the equation. So for example, let me just say in general, supposing there were two inductances L1 and L2. These two inductances L1 and L2, if they are magnetically coupled, what that means is if the flux that is produced by one links with the other, in that case they are said to be magnetically coupled. And when they are magnetically coupled, there is a mutual inductance. That means this is the mutual inductance that results in a flux produced by one, or rather flux linkage. I keep saying flux, but it's actually flux linkages. That is, the flux linkages of one inductor due to the current flowing in the other inductor. And we denote this usually by M. Or you can be specific and even say M12, M21, but we usually just write as M in most cases, because in most cases, the effect that one inductor has on the other is usually the same as the effect that the other has on this one. It's only in rare cases that one has a different effect on the other inductor versus the other having a different effect on the other inductor, right? So usually we can just specify as M. Now, what does this mean? What this means is that if I were to say the flux linkages of inductor 1 will be equal to L1 multiplied by I1 plus M into I2, right? So this means that the flux linkages of one inductor are not just produced due to the current flowing through the inductor, but is also due to the current flowing through the mutually coupled inductor. This is the case with any mutually coupled magnetically coupled circuit. And in the case of an induction motor, that is also the case. So for example, if I say psi I2 will be equal to L2 multiplied by I2 plus M into I1. That is, both the flux produced by both these inductors are influenced not just by the current flowing through them, but also the current flowing through the magnetically coupled inductor. And that magnetically coupled inductor has this mutual inductance M. And the question is, what is this M? This M is usually expressed as M is equal to K into square root of L1 multiplied by L2. Right? So this K is the coupling factor. And what this means is how much of the flux produced by one inductor links with the other. Because remember, not all of it will be linking. Some of it will be wasted. There will be leakage. So this K takes into account the leakage that is present in any magnetically coupled system. So usually, if you have a fairly well coupled system, this can be anything in the range of 0.95 to 0.99. You usually don't take it as 1 because there is always some amount of leakage, right? You can even take it as 0.95 or something, whatever. Now in the case of an induction motor, because there is an air gap, there will be, you can assume something of 0.98 or so, right? So you can say around 2% of the flux produced is leaked, goes into leakage, does not associate with the stator or the rotor, but rather is leaked into the air. So this is how we usually express any general magnetically coupled system, right? We say we know the inductances, these are the self-inductance. The self-inductances are, and there is a mutual inductance which can be expressed with respect to the self-inductances, taking into account the coupling factor. And once we have this, we can write the equations for this magnetically coupled circuit. These are the flux linkages. Now the question is, what are we going to do about this? Here, in the case of a stator and rotor, because we have taken into account the leakage inductance of the stator and the leakage inductance of the rotor, we do not need to consider this coupling factor because leakage is taken into account independently. So then the question is, how do we write this mutual inductance? The mutual inductance is merely equal to square root of LMS multiplied by LMR, right? So this is the mutual inductance in the case of an induction machine. If you want, you can give it a subscript saying MSR. This is the mutual inductance between the stator and the rotor. So now that we have this, we can write exactly the similar equation for this stator as well. So for example, I can just copy this and place it here, and I can say psi S, which means stator, is equal to the total stator inductance, that is LLS plus LMS, multiplied by IS, and this is important because this is the stator flux, this is the complete stator flux, plus MSR multiplied by IR. Okay, and I can also copy over this equation, place it here, and I just have to change the subscripts and say that this is the rotor flux. The rotor flux is the complete rotor inductance multiplied by the rotor current plus the stator, this mutual inductance multiplied by the stator current, right? These are our flux linkage equations of the induction motor. So now the question is, now that we have the stator inductances and the rotor inductances, what does it actually mean in terms of the torque that we were talking about in the previous lecture? So this I will talk about later in the next lecture because this lecture has already gotten pretty long. But what is important, and this is what we need to do, and we will also do this in the next lecture, is we need to map what are the relevances between all these parameters that we are talking about here versus the parameters here, right? You might think that we've introduced very different parameters, but in reality we have not. And all we are doing is we can use all these parameters here of the equivalent circuit, which we have already calculated, which we have already talked about, and which we can determine for any motor using simple experiments. And these parameters we can use in our new dynamical equation mathematical model. And as we go ahead, we will introduce more and more equations, especially equations that help us to determine the torque produced because of the interaction between these fluxes. This will come in the next lectures. It is going to take quite a while because, as I said, this concept is a bit complicated. At least I spent a lot of time breaking my head over this. Therefore, I do not want to rush through just by writing equations, but rather would like to take some time and try to describe how all these equations come into being and to actually represent an induction machine. So, if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this lecture. Thank you so much and see you soon. Goodbye for now.